Hello and welcome to Statistically Significant. In this session, I'll be discussing about the Anova techniques. Now, in my previous two videos, I have discussed the one-way Anova and the two-way Anova without replication. Now, some of my viewers, they gave me a suggestion that I should discuss a bit of theory before getting into the Excel statistics tools. So now, I am doing a bit rewind of the first two videos. Now how to do the one-way Anova. Let's see. First, just have a look at the theory. Our model for the one-way Anova is this. It's Yij equals to mu plus alpha I plus Eij, where Yij is the jth observation corresponding to the ith level of the factor A. Mu is the general effect, alpha I is the additional effect due to the ith level of the factor A. Eij is the inherent error in the model which follows independent identical normal 0, sigma square. Now, what can be the application of Anova? Why are we using Anova? See, if we consider an example, let Yij be the performance of any player who has been selected for the Indian national team. In cricket team I am talking about. So what could be our general effect? The general effect is that yes, he has gone through playing through the state levels, the Ranji levels, and he has qualified to play for the Indian team. That's the general effect. That's every player goes through this. Now what could be the additional effect which will be affecting his performance for the Indian team? Our response Yij is the performance in the international level for that player. What could be that additional effect? Yes, that additional effect could be the time he spends in the nets. Like you see the bowlers, if you consider the batting performance, the bowlers spend the least amount of time at the nets, and the batsmen, the openers, the middle order, they spend the maximum time at the nets. So our levels for this additional factor A would be the time spent in hours in the nets, and we know that every model has an inherent error, so Eij is the error. So what would be our null hypothesis here? It would be alpha I equal to 0 for all I, that is, there is no additional effect on the performance of the player in the international level due to the factor A, that is due to net practice time. And our alternative hypothesis would be alpha is not equal to 0, that is, yes, there would be a significant effect on the performance of the player due to the time spent at the nets. And what would be our test rule? If f observed, that is, we would see it later while computing, is greater than the f critical value. The critical values are the statistical values obtained from the statistical tables. Now if the f observed is greater than the f critical value, then we reject the null, and otherwise we accept it. That is, if the f observed is less than the f critical value, then we accept the null. So now moving on to the usage, how we do it in Excel. I'm doing it again. So now in this problem we are given the life hours of bulbs. Our response is the life hours of the bulbs, and the additional effect, the factor, is the different batches in which the bulbs have been produced. So our response is the life hours of the bulbs, and the additional effect is the effect of the batches, the different batches in which the bulbs are produced. Our null hypothesis would be the average life hours of the bulb is same, or it could be written like this, that there is no additional effect due to the production batches. And our alternative is that the null is false, that is, yes, average life hours is not same, and yes, there is a significant effect on the life hours of the bulbs due to the batches. So now how are we going to do it in Excel? Have a look. We go to the data tab, data analysis. We select the Anova single factor. We have just one factor here, that is the batches. So okay, select our input range, do it like this. Grouped by columns, yes, see they are the columns A, B, C, D and D. Labels in first row, yes, definitely we have the labels in the first row. Alpha, it is a level of significance 0.05. The output range, select this cell and let's go. Yes, we have got our results. Let me just adjust a bit. Now the main important part is the Anova table, and now I am going to interpret the terms for you. The source of variation, yes, the between groups are the effect due to the batches. The between groups are the effect due to the batches, and within groups are the errors. SS means the sum of squares. This is the sum of squares due to the batches, and it is the sum of squares due to the errors, SSE. DF is the degrees of freedom. The total, now how these are 3, 22 and 25, let me explain. See, totally we have here 26 bulbs. If you count it by hand, you could see there's 26 bulbs here. So the total DF becomes n minus 1, that is 26 minus 1, 25. We have 4 groups A, B, C and D. Yes, we have A, B, C and D, and that's 4 minus 1, 3. So that's 25 minus 3 gives the error DF 22. Now what is MS? Is the mean sum of squares, which is obtained by dividing the sum of squares corresponding to their DFs. That is, SS for batches is obtained by dividing this 44,360.705 divided by 3, it gives us this value, and dividing this SSE by this DF22 gives us this value. And what is this F? This is our F observed. See, this is our F observed. It is obtained by MSB by MSC, MSB by MSC, that is MS between the groups, that is MS between the batches, and MS errors, MSE, and we are getting it 0 and it is written 2.149. Our F critical value is 3.049. These are the statistical tables. This value is that F 0.05, that is at level of significance 0.05 with DFs 3 and 22. This value is 3.049, and now we are going to observe that this observed F is less than the F critical value. So we fail to reject the null. Our conclusion is that we fail to reject the null, and we have to accept the fact that the average life hours of the bulbs is same. There is no additional effect due to the batches of production. These are different batches of production. Now this interpretation could be done in another way using this p-value. See, our level of significance is 0.05, and this given and the observed p-value is 0.12, which is greater than 0.05, and thus we fail to reject the null. That is, we have to accept the null, because the lesser the p-value, I repeat, the lesser the p-value, the greater the evidence of rejecting the null. Here the p-value is greater than the the p-value is greater than the level of significance. So we fail to reject the null, and we have to accept the fact that yes, there is no effect due to the batching of the bulbs, and the average life hours of the bulbs is same. Now moving on to the two-way Anova. With one observation, I did this in the previous video. I am going to explain the theory a little bit and then again do the problem. I know it's a bit awkward, but I just want to explain it in a better way. Now see, for the two-way Anova model with one observation per cell, we have the model is yij equals to mu plus alpha I plus beta j plus gamma ij plus eij. That means the general effect. Alpha is the additional effect due to the ith level of factor A. Beta j is the additional effect due to the jth level of factor B. Now gamma ij is the effect due to interaction of A and B, which we assume to be 0. Now I'm coming why it is 0. Eij is inherent in the model. We have error in every model in statistics. That's not a different issue. Now why are we taking this gamma ij as 0? Because see, we have just one observation per cell. Corresponding to the two factors, we have just one observation per cell we are taking. We cannot replicate that observation. So as we cannot replicate, we are not getting a better estimate about the interaction of the two factors. It's an important assumption. When we are capable of replicating, we get a better estimate of the observation of the responses. But when we cannot replicate, we cannot consider the interaction factor, and we have to take it as 0. When we will be doing the two-way Anova for m observation per cell, in that case we will have replications corresponding to the two factors, and in that case we won't consider this gamma ij as 0, and we will incorporate in our model. So now what is our null? We want to test that yes, there is no additional effect due to the ith level of factor A, and against that yes, there is a significant effect on the response yij due to this factor A. Our second null hypothesis is that there is no significant effect due to the factor B. Against that yes, there is a significant of the factor B on the on the response. Now what's our test rule? We reject the null if the f observed values exceed the f critical values, and we accept it otherwise. So now here we know that we're given that the capital A, B, C, D, A, E, they are the professional raters, and the small a, b, c, d, e up to j are the 10 service station. The entries in the cells, they are the ratings, and the reason why we are using the two-way Anova here is that yes, the ratings are affected by two factors: the raters, the professional raters, and the service stations. So now our null here corresponds to that. There is no difference between the raters, that is, there is no significant effect on the ratings, on these ratings due to the raters. Against that yes, there is a significant effect due to the raters on these ratings. Our second null hypothesis is that there is no significant effect on these ratings due to the different service stations, against the alternative that yes, there is a significant effect on the responses, on the ratings due to the service station or different service station. And no interaction is assumed. So now we will be using this Excel data analysis. Solve without replication. We don't have any replication here. Okay, we select our input range. Yes, there are labels. Level of significance 0.05 alpha. Output range. Select this. Oh, sorry. You have to be a bit of careful while doing this. Yes. Okay. Yes, there we go. We have our Anova table. So now yes, the rows, now we consider the source of variation. The rows are the professional raters. See, A, B, C, D, any in caps, and the columns are the different service stations here. I've explained what is SS, DF, MS. Now how do we get this? Totally we have 50 service stations, so 50 minus 1, 49. We have 5 rows, we have 5 raters, that's 5 minus 1, 4. 10 columns, we have 10 service stations, 10 minus 1, 9. So 9 plus 4, 4 is 13. 49 minus 13 gives 36, that's the DF for the error. Now this F, the F observed, we get this by dividing the MS rows by the MS error, that is MS of the raters divided by the MS errors. We get this F by dividing the MS columns, that is the MS service stations, by the MS error. Now for this particular F observed value, it is less than the F critical value, so we fail to reject the null again in this case. That is, there is no significant effect on the ratings due to the different provisional raters. And for this observed value, which is exceeding this F critical value by a large amount, we have to conclude that yes, there is a significant effect on the ratings due to the different service stations. And also this interpretation could also be done with the help of these p-values, or p-value 0.05. This p-value is exceeding 0.05, so we fail to reject the null and we accept the fact that there is no significant effect on the ratings due to the different provisional raters, and this p-value is less than 0.05, so we have to reject the null and conclude that yes, that there is a significant effect on the ratings due to the different service stations.